All set?
Yes.
Okay, great. Welcome everyone to today's seminar on non-emission physics. We have the great pleasure of welcoming Professor Benedetta Flebus from Boston College. Before we get started with the seminar, let me quickly remind you of our house rules. All of our talks are recorded and made available on YouTube, so please bear this in mind. Please keep your camera and microphone switched off during the talk. There will be a Q&A session after the talk, and you can either write your questions in the chat and we read them out to the speaker, or you can raise your hand and ask your question live on Zoom. If you're joining us on YouTube, you can just write your question into the live chat and we will also pass it on to the speaker. So now let me introduce our speaker today. Professor Benedetta Flebus received her PhD from Utrecht University in 2017. After two postdoctoral fellowships, the first a Rubicon postdoctoral fellowship at UCLA, and then a postdoctoral fellowship at University of Texas at Austin, she became assistant professor at Boston College in 2020, where she still works as PI to date. She received two prizes for her work last year. She received the Mildred Dresselhaus Junior Award and the NSF Career Award. So it's a great pleasure for us to welcome you to the seminar series, and we're very much looking forward to your talk on non-emission physics and magnetic systems. Thank you very much, Benedetta.
Thanks a lot, and thanks a lot for inviting me, Claire. It's really nice to see you again. So let me set up here my screen and get started. So I'm going to talk about some of the work that I've been doing, among other things, in the last I would say 3 years or so. So there are a lot of people that have been contributing to this work. I'm not going to mention them all, but you can see their pictures here. And generally what we did, I would say broadly, was to explore magnetic systems from a non-Hermitian perspective. So how did this start? So something that we have been looking at from, let's say, more the perspective of spintronics was topological phases in magnetic systems. So of course, after, as you all well know, there was so much interest and so many discoveries in the context of topology applied to electronic systems. People just started naturally asking themselves whether we can find the analog of these topological phases in magnetic systems. So there have been a lot of proposals in this respect, and a lot of really interesting works in which people managed to pinpoint which type of interactions are capable to give you a topologically non-trivial band structure in a magnetic systems. However, I would say that a limitation of these works is that they were really inspired by all the efforts that have been done in the context of electronic systems, where someone would just naturally use an Hermitian Hamiltonian. But while electrons have, I would say, almost an infinite lifetime, magnons instead are excitations with respect to the ground state of a system. So since nature just naturally wants to be at equilibrium, what really happens in real materials is that it's full of spin non-conserving interactions that will eventually dissipate magnons and try to restore the ground state in a system. So how do you describe all these spin non-conserving interactions? So in other words, how do you describe the dissipation, the finite lifetimes that magnons are subjected to? So as I will try to show you here and there today, this is actually a really complex question that is very material dependent, and at least to my knowledge, has not really been properly answered yet. But we have definitely some simple phenomenological tools to describe dissipation in magnetic systems. And I would say the most well-known one takes the name of Landau-Lifshitz-Gilbert equation, so LLG equation. And here, what you're doing is to take for example, a ferromagnetic system and describe all these collections of spins of localized moment as a giant macrospin. Now, this giant macrospin is experiencing all the effective fields that are exerted on it. But eventually, even if you tilt the spin away from equilibrium, you know that it will relax back to its equilibrium position. And that's what this term, which is called Gilbert damping, does. It really restores the equilibrium position of the magnetization. So in other words, it dissipates magnons. Now, this is, at least that's something that I read often, is one of the most nonlinear equations that you will find in condensed matter. But what we usually do, and I will show you more details later, is to linearize this equation. So we just focus on very small fluctuations around equilibrium. We call this deviation from equilibrium magnons, and we can recast this equation in the form of a Schrödinger equation and identify an Hamiltonian. And what's interesting and what we have realized only in very recent years is that this Hamiltonian is naturally a non-Hermitian Hamiltonian because of these dissipative terms. But people for a long time didn't know, especially in our community, how to treat a non-Hermitian Hamiltonian. Even just this word didn't really make sense to a lot of people. So this term is usually neglected. It is, at least in this proposal, by assuming that you can find the material that has very, very small dissipation. Instead, we started looking at these non-Hermitian Hamiltonians, and of course, it was also a great time to do that because there were this wonderful, I would say, seminal works from, for example, Sato, Ueda, and many others, in which they started looking at non-Hermitian Hamiltonian, and they realized that the properties of these Hamiltonians often are not just a trivial generalization of their Hermitian counterpart, but instead they can be really unique. And probably you know this topic even better than I do, but some of the examples are, for example, these lazy nudge states that can be found in systems that really resemble in many ways Hermitian systems. And something I would say a completely other end of the spectrum is the skin effect, which is a property that is really unique to non-Hermitian systems. And something that is quite ubiquitous are exceptional points, which are these spectral degeneracies of non-Hermitian systems. So what we realized is that magnetic systems, in terms of at least a solid-state system, seems to be a really good candidate for non-Hermitian engineering. And the key ingredients that are necessary to do that are pretty simple. What you need is to have loss, but that's something intrinsic to any magnetic system. It's actually something that we try to get rid of for a long time, but it's not really possible to achieve a lossless limit. And what you want to also be able to do is to control gain. So in the context of magnetic system, controlling gain really means being able to inject magnons, so inject pure spin into the system. But this is something that in the spintronics community we know very well how to do. So there are several established experimental techniques to do so. So we looked at these key ingredients. We also wrote a review in case any one of you is interested in learning more details about this. And what we managed to identify are both topological magnonic phases in terms of in dissipative magnetic systems. We also try to understand what exceptional points really mean in the context of magnetic system. And we also try to understand whether magnetic systems can display the non-Hermitian skin effect. And once again, what this really means in terms of experimental observable. So I will not have the time today to go through all these topics, but I will try to give you, an idea of the advantage of describing magnetic systems under non-Hermitian lenses in terms of the topological phases that can be unveiled. And I will also describe what are the key ingredients to find the non-Hermitian skin effect in magnetic systems. So this was our first work in this context. And what we tried to do was to understand if we can engineer an archetype of non-Hermitian topology in a realistic magnetic system. So initially our proposal concerns spin torque oscillators, which I imagine is something you might not be familiar with. But later we also realized, and now we are trying to build with some experimentalists, that this can also be engineered in some relatively simple magnetic multilayer. So the building block for this idea, it's a magnetic layer in which you are capable, in a way or another, of injecting spin current. So how do you describe this magnetization dynamics? You still, of course, use the LLG equation. This is the simplest way to describe this system. And here you have this term that comes from the effective fields that are exerted on the magnetization and really determines what is your ferromagnetic resonance frequency. So what is the Kittel mode of your magnetic layer? Then there is damping. And then since we want to really do some non-Hermitian engineering, we also have the possibility of injecting magnons and creating gain in the system. So you can do that via this so-called spin torque term. And what you really need from a physical point of view, it's a spin current that is polarized in the right direction. This is something that it's really fairly straightforward to do. And as I already anticipated, we want to realize a non-Hermitian SSH model and understand how this model behaves in the context of magnetic phases. So the starting point is the LLG equation. And then what we do is to set ourselves in the linear regime. So setting ourselves in the linear regime simply means that what you say is that there is a magnetic field that polarizes your system along, let's say, the z-axis, and then you allow for only small fluctuations around this axis. So, and then whenever you plug this solution into your equation, you retain only linear terms. Then you will map this deviation from equilibrium into magnon operator. This is a very standard thing to do. And what you obtain, it's a non-Hermitian quadratic Hamiltonian. So here you have the characteristic frequency of the system that contributes to your Hermitian component. And here, as you can see, you have a term that is non-Hermitian and simply describe the interplay between the intrinsic loss that you have in the system and the gain that you can create with the spin current. So then what we want to do is to also have something topological. And what you have to do most of the time in order to do so is to have a unit cell that has more than just 1 degree of freedom. So we just imagine that if we create this magnetic heterostructure, we can separate the layers that are described by the LLG equation that I just showed you. Let's call them SOT-A and SOT-B, by some metallic spacer that can also be used for spin injection. And you can vary the thickness of this metallic spacer such that your unit cell will be comprised of both this element and this element. And metallic spacers in magnetic heterostructures are known to mediate a coherent exchange coupling via the RKKY interaction. And then the last thing that we have to do, which is of course very easy to do in theory and definitely a bit more complex to do in an experiment, is to control the gain and loss within each unit cell. So what we are thinking of doing is to inject a lot of spin current in the A sites and no spin current at all in the B sites. So already now, and I think this is a key point, what you would imagine that this system does is the following. You would imagine that here, since you are injecting a lot of spin current, such that not only compensates the loss of this magnetic element, but actually creates net gain, you would expect that in every magnetic element where you're injecting this large amount of spin current, the magnetization dynamics activates. And as we will see, this is not exactly what happens, and this will be a signature of topological behavior. Now, we also want first to start with the simplest model. So we are working in the PT-symmetric limit. We are assuming that the gain is equal in magnitude at the A sites to the loss that you can find in the B sites. And then we also explored in some subsequent work, various deviation with respect to this perfectly tuned spot in the parameter space. Then we derive the quadratic Hamiltonian for this coupled system, and we simply exact diagonalize the system. So, but since this is a seminar on non-Hermitian phenomena, I imagine that you might be familiar with this model. What we find is that by varying the thickness of the metallic layers that are separating our magnetic elements, we can access different topological phases, both topologically trivial and non-trivial. So here you find this PT unbroken phase in which we have two edge states. These edge states just really correspond to some magnons at this site and this site. And the bulk spectrum, it's purely real, right? Because you can always support the stationary solution in a PT-symmetric model. And the edge states will come as a complex conjugate pair. So one edge state will be subjected to gain, obviously the one in which you're actually injecting spin current, and the other one will just be purely lossy. And then as you keep changing J over J tilde, you will enter a PT broken phase, which is still topological, but now, as you can see, the bulk spectrum becomes degenerate with your edge states, and your bulk states start acquiring some imaginary component of the energy. And here, instead, you're in a completely boring topologically trivial phase. Now, just to anticipate what I would say, it's maybe the most interesting part of this work. What we will find is that because of this edge state that has some positive imaginary energy, while the bulk has a completely real spectrum, it's because of this property that we will find a really clear signature of topological magnons. And what I usually say is that this Lezin edge mode really beats the Bose-Einstein distribution. What do I really mean with that is the following. So people have been looking at a topological magnonic system for a long time. So there are a lot of theoretical works that are focused on this topic. But actually, there is quite a consensus that up to now, there is not yet a clear experimental signature of magnon topology. And it's quite simple to understand the reason why this happens. So if you think about it, what really plays an important role in this context is that magnons are bosons, so they're controlled by a Bose-Einstein distribution. So if you try to, for example, search for some signature of magnon topology in transport, you really run into a problem that does not exist in fermionic system. So in fermionic systems, if you have some edge state that are propagating, what you can do is to simply set your Fermi level in the middle of the gap, and then especially if you cool down the system, you will find that these are the only states that are contributing to transport. But instead, what happens in a bosonic system is that there is obviously no Fermi level. So even if you find, in theory, these topological Hermitian magnon bands, then you need to populate them, but you will populate them according to the Bose-Einstein distribution. So you necessarily have to start populating also all the bands below. And these bands below might not have a finite Scher number, but can always have some Berry curvature contribution that is not trivial. So they necessarily will contribute to the thermal hole current. And therefore, it's really quite hard to be sure that you're probing topological magnonic edge states. And then there are also other complications, such as the presence of phonons, which can be chiral in a lot of materials. And also magnon polarons, by definition, tend to be topologically non-trivial. So in other words, it's really, really hard to point at some experimental data and be able to say that these are topological magnons. But I will show you that through this non-Hermitian engineering, there is actually a much more obvious experimental signature of magnon topology. So what you're going to do in an experiment, obviously, is not you're not really going to probe this quadratic Hamiltonian that you derived by linearizing the system. What you're going to probe is the actual nonlinear LLG classical dynamics. So now what we did was to go back to our initial nonlinear equation of motion, and we asked ourselves whether, if by tuning the parameters be exactly at the point in which our quadratic Hamiltonian was displaying some topologically non-trivial property, we can identify some experimental signature of it in the nonlinear LLG dynamics. So what do you expect naively in this case is that since you are pumping spin current at all the A sites, and this spin current is actually very large, you would just expect that all the A sites start undergoing some precession. And interestingly, this is not what we observe. So we ran this simulation for 20 coupled magnetic elements. And when we ran this simulation, we set our J and J tilde such that we are in the PT unbroken phase of the linearized quadratic Hamiltonian. And what we see at the level of the nonlinear dynamics is that despite spin injection that is occurring at all the A sites, only the magnetic element at the edge starts undergoing precession and in theory emitting topologically protected microwaves. And we ran this simulation really a number of times, and for a very, very long time, the only thing that you see is the dynamics of this lasing edge state that survives even in the nonlinear in the nonlinear LLG. We also, of course, wanted to check whether this was just a coincidence. So we started moving in terms of parameters in our simulation away from the PT unbroken phase, and we entered, for example, here the PT broken phase, where you see your bulk states are acquiring some finite imaginary energy that is reflecting the fact that you're pumping spin current in alpha of them. And indeed here the dynamics changes. So you still see your magnetic element at the edge undergoing precession before everything else, but eventually also the bulk, all the A sites are getting excited. And I'm not showing the plot here, but if you move away from a phase that has a topologically non-trivial character, what you see is exactly what you would expect, from an Hermitian classical LLG perspective. So you just see that all the A magnetic elements start undergoing precession. So we also investigated how robust, obviously, these signatures are. So we looked at some experimentally relevant perturbation, and also, of course, at the role that, for example, temperature, which is always going to be present in this type of experiments, can play. It's very hard to give a sharp guideline. It really depends. All this dynamics is varying continuously. But I would say that generally these effects are really quite robust, and hopefully they will be soon engineered in a real system. So what I think maybe are the most important takeaway messages from these first projects that we did in this context is that really the clear experimental signature of magnon topology emerge from accounting for this non-Hermitian component, and that in general we always thought that the magnetic dissipation was something that we kind of had to get rid of, but its inclusion allows us to unveil new phenomena. And then let me maybe go really quickly over this part, otherwise I will use way too much time. But something else that we looked at is the non-Hermitian skin effect. So perhaps I don't have to really explain you as an audience what this effect is, but it really stems from the breakdown of bulk edge correspondence, and it's characterized by a topological invariant, though yet it's not, at least to my knowledge, fully clear how robust this is in the characterization. So the non-Hermitian skin effect is generally a manifestation of non-reciprocity in the system. And there are, of course, different ways in which you can engineer non-reciprocity. So you can make your coherent coupling or your dissipative coupling non-reciprocal. But this is not the only way to engineer non-reciprocity. Another way really lies in balancing coherent and dissipative interaction. And I will show you that this is actually how the non-Hermitian skin effect occurs in magnetic systems. So the first issue that we had in order to start exploring this effect in magnetic system was a description of dissipation. So how do we include the dissipation in a lattice model? The only way in which dissipation has been really treated in the context of magnetic system is, I would say mostly in the long wavelength limit. And therefore, we had to come up with a strategy that was not microscopic, that would have taken way too much time, and perhaps not even been so effective. What we decided to do is to use a phenomenological approach. So in other ways, our idea is that in experiments or in ab initio calculation, people would look at how some mechanisms, for example, magnon-phonon interactions, can drive magnetic dissipation. And then they will provide, for example, for the acoustic and optical mode of an honeycomb lattice, some result that we would include in a lattice model. So we just make an ansatz that is consistent with the fundamental symmetries of the system. in this case, the C3 and translational symmetry of a magnetic honeycomb lattice. And then we use these parameters in order to fit the experimental or ab initio curves. And this is written in terms of the eigenmode of the system, but you can always go back to the real lattice spins and look at this term. And these terms are really telling you that the phonons are known to modulate the exchange coupling between two spins. And now, there will be an adiabatic contribution to that is perfectly coherent, but there can be also a dissipative contribution, which is contained here. And then we wrote down this model and we looked at whether the non-Hermitian skin effect was present or not. So what we did was to follow the guidelines proposed in this work. So we really look at whether in 2D, we are looking at an honeycomb lattice, so it's a 2D system. We look at whether our periodic boundary condition spectrum has a final spectral area or not. And this is a principle proposed in this work, which we find to work pretty well. So if we populate our system up to here, where there is a line, we do not really see any skin effect. We really see block waves that are spread throughout the bulk. But if we start populating the magnetic system up to here, we start seeing the skin effect. Then we looked at our model and we tried to understand where is the skin effect coming from. So what we find are that there are two fundamental interactions that we need to have at the same time in order to see the skin effect. So first of all, we need in our case, because we were considering these van der Waals materials that usually can support, because of inversion symmetry breaking, some chiral spin interaction, we consider this Dzialujinsky-Moria interaction. It's an interaction that looks a bit like a magnonic counterpart of the next to nearest neighbor hopping of the Haldane model. And we also need non-local dissipation. But at this point, we were not really able to understand why. What is really the underlying mechanism? So we ran a lot of symmetry checks, but we didn't really find, something that could answer fully our question. So the DMI breaks the time reversal symmetry of the Magnon-Hamiltonian. But if you have DMI only and non-local dissipation, the skin effect doesn't happen. So what we did was to try, to take a step forward and both understand why these interactions are necessary. And also what we wanted to understand is, whether the presence of the non-Hermitian skin effect at the level of a Magnon-Hamiltonian can actually lead to some observable experimental signal. So let me try to be even more quick about this part, but the essential thing that we did was to identify a system, a very simple system. So just an array of macrospins connected to some featureless buff, and identify the key symmetries that allow us to have a non-Hermitian Hamiltonian in our now master equation approach that can display the skin effect by virtue of the same ingredients that we found in our previous work. Obviously, this master equation cannot be solved for a system of classical spins. However, we can still access via cumulant expansion the dynamics of higher order correlation. So we can also look at corrections away from the non-Hermitian approximation. And so we found indeed a very simple system that can display an Hamiltonian with both DMI interaction and non-local dissipation, whether you have only axial symmetry along the z-axis in spin space. And then we looked at the winding number and to find that, well, there are different limits, of course, for this winding number. So for example, when your symmetric exchange is very strong with respect to the parameters that allow you to have a non-Hermitian skin effect, your loop does actually squeeze. And this will also have some obvious consequence in terms of experimental observable. And then something else which is actually very trivial that we noticed is that this 1D number, it's independent of the local dissipation that every macrospin feels. However, imagine that I create a magnon at this point. If now the local dissipation is really strong, this magnon will never propagate and will never give rise to any non-reciprocal spin current that could be a smoking gun of the presence of the non-Hermitian skin effect. So we also ran some simulation of our dynamics and as expected, that's what we see. Even when your winding number is finite and this loop is actually perfectly circular. Of course, if there is a lot of local dissipation, you cannot observe spin waves propagating in any case, in any way, neither reciprocal or non-reciprocal. So from a very practical context, this also made us ask what's really the meaning behind this winding number whenever you're thinking about actual experimental observables. Something inside a bit, let's say, something really interesting for us was, in this case, understanding how this non-reciprocity comes about. And interestingly, this is also related to something that is very different. So all these approaches to reservoir engineering and chirality engineering in open quantum systems. So what happens here, if you just focus on two macrospins, is the following. There is some exchange interaction, right? Some coherent exchange interaction between them, mediated by this buff. This buff could be a metal, this could be an RKKY type of interaction. And then there is DMI. So here, notoriously DMI comes with an imaginary unit. So in this sense, it's very similar to the couplings in the model of Haldane. And here we have also, of course, coming with an imaginary unit, but also being non-Hermitian, we have some non-local dissipation that is coupling as well these two macrospin in our model. And what we find is that when DMI and gamma are different from zero, we have some non-reciprocity. And you can see it quite easily, right, by looking at this 2x2 Hamiltonian. This is the likelihood of going from this spin to this spin and vice versa from this spin to this spin. So here you can really change gamma by changing D and vice versa. And this will give rise to two different matrix elements. And then you have also a very special case. So if you completely neglect the symmetric exchange interaction and you set D equal to gamma, you have a fully unidirectional system. So here clearly the key ingredients are again the same key ingredients that we found in our previous work, but I would say now understood much better. So we need something that is non-Hermitian, let's say this non-local dissipation. Otherwise, these two elements in the absolute value would be exactly the same. But we also need something that comes with a phase that then will give rise to this imaginary unit that compensates this gamma, a phase that should be non-trivial. So a phase that, in other words, we cannot gauge out. And this is intimately related to time reversal symmetry breaking in the system. And that's what the DMI does at the level of the Magnon Hamiltonian. And then to end, we try to understand if we can connect this toy model that we use to understand better the non-Hermitian skin effect. If we can connect it to something more realistic and also something that it's somehow more accepted within the spintronics community rather than a toy model, we can, for example, find the same effect in a magnetic multilayer, where the spin dynamics is described by this LLG coupled equation. So what we need are, again, DMI and non-local dissipation. But non-local dissipation, it's always happening in these systems. So this is something very well known that was described already 20 years ago. So what happens is that if this spin is precessing, it can pump spin angular momentum via metallic spacer into the adjacent magnetic layer. And this is, of course, a dissipative term because there is actual loss and injection of magnons from a layer to another. And also, if you break some symmetries and build these interfaces in a specific way, you can have some interfacial DMI between these two. So imagine that this metallic spacer is mediating many interactions. It's mediating an RKKY interaction, which is just a symmetric exchange, and it's mediating also the anti-symmetric part of the same interaction, which is the DMI. And so what we find is that indeed, even at this level, we can find some finite winding number. It's not really going to be a circle for a detail that maybe might be too technical if you don't work in magnetism, but it's simply because here the dissipation always depends on the instantaneous state of the adjacent metallic layer. So somehow these dissipative terms are not just coupling nearest neighbor, they are indirectly coupling next to nearest neighbors. So you can never achieve this fully unidirectional limit, but you can definitely create non-reciprocity. And what really happens at the level of this magnetic system is that if you excite some spin waves in the middle of this multilayer, this spin wave will propagate in a non-reciprocal manner. And that should be your signature that at the level of a quadratic Hamiltonian, the non-Hermitian skin effect is present. So with this, I came to the end. What I tried to briefly show you today is that we found, we looked at topological non-Hermitian magnetic phases, and we also identify some signature of the non-Hermitian topology in the nonlinear magnetization dynamics, which is what actually you will measure in an experiment. And this clear experimental signature really comes from keeping track of the non-Hermitian component, meaning dissipation of the magnetization dynamics, which has been ignored for a long time. We also identify the key ingredients for the non-Hermitian skin effect in magnetic systems. And it should be a quite ubiquitous effect because what you need is non-hermiticity, which is always there, and you also need some, I call them time reversal symmetry breaking at the level of the Magnon-Hamiltonian, but this means that at the level of a classical spin model, there is some inversion, lack of inversion symmetry in real space, which is something that happens pretty often. However, whether you can observe this effect or not really depends on your parameters. It cannot be predicted by this winding number. And I would say that definitely this work is motivating us to try to find a more comprehensive description of dissipation in the magnetization dynamics. So for example, try to really reconcile these classical nonlinear equations that we have been using for decades with some more microscopic treatment coming, for example, from master equations. So that's something that we are working on. So yeah, thank you for the attention.
Thank you very much for this very interesting talk, Benedetta. I'm sure there are questions. Otherwise, maybe I can start. In particular, So let's start. No, we have a question. So yes, feel free to unmute yourself.
Yes, hi, very nice talk. I have maybe rather a conceptual question. So usually, you know, if I think about the magnetism, that is, of course, comes from electrons, right? So in principle, if I'm considering a magnetic insulator, that typically means I have a gapped fermions, and usually I have to integrate the fermionic degrees of freedom to get a magnetic or purely a local spin type of the Hamiltonian. So I was wondering in this case, so in your case, from what you presented, somehow I get the feeling that you introduce a non-Hermitian term in such a phenomenological way. So basically, still assuming that the fermions are still, you know, completely Hermitian. Or is there a way to show that you can start from initially non-Hermitian fermionic Hamiltonian, and then you can integrate them out for a gapped phase and get a non-Hermitian version of the spin Hamiltonian? I don't know. I didn't thought about this.
No, yeah, that's a really good question. So yeah, definitely this. So for example, Gilbert damping was introduced phenomenologically by Gilbert, and then if you want to look at one of the sources of this damping is definitely some spin orbit interaction that is happening in a system. So I think it's definitely possible to start from right. You could definitely start from the description of the fermionic system, and then you know, eventually integrating out degrees of freedom. That said, to my knowledge, no one has done this. I think it's really fairly complex.
Yeah. Okay. Thank you.
But you could definitely do it.
Okay. Thank you.
We have another question. Would you like to unmute yourself?
Yeah, hello. Yeah. Hi, thank you for the talk. It was good indeed. So I have two short technical questions. Can you just go back to the plot of that OBC versus the periodic boundary condition, real versus imaginary one?
Yeah, this one.
No, the edge states one. Previously, I think.
Oh yeah, yes.
Yeah. This one. Yeah, just.
Yeah.
Yep. Thank you. So I see that on PT broken phase, you know, that is the right hand side plot is, I think, the bulk plot of imaginary energy versus parameters.
Yes. Yeah.
Yes, this is the one is a bulk plot and another is a boundary plot, isn't it?
So these are the bulk states, right? So so these are, let's say, think about it as like the frequency of the magnons associated with these elements, and these are the edge states, which are really here. Yeah.
And I was asking about the right hand side plot of imaginary energy versus the parameter. Is that plot coming from the bulk? I think that plot is coming from the bulk, I think. Or boundary.
Let me see if I understand the question exactly. So this is the same. So this is real, and this is imaginary. This is exact diagonalization of, let's say, 20 of these states, and this area is exactly the same area. So what happens in the PT unbroken phase is that your bulk states, they will have some, real energy, but you see now I have all of them are collapsing on the same line, because in virtue of this PT symmetry, they do not have any imaginary energy. And the edge states are come. It's really a property of the PT symmetric Hamiltonian. They come as complex conjugate pair. So you will find that they have the same energy. So these are two, but they collapse on the same line. And then one has a positive imaginary energy, and the other one negative. Yeah.
Okay, I understand. And do you have any exceptional points in the bulk corresponding to these plots?
Yeah. Yes. So here you are going through an exceptional point.
So you have 4 exceptional points in the bulk.
No, we have two exceptional points in the bulk.
Exceptional.
So an exceptional, right? Because an exceptional point at the level of like let's say the bulk Hamiltonian, right? So bulk Hamiltonian means that we don't know anything about this leasing edge state. Like you close the boundary. So the exceptional point is where you go from or real to complex conjugate. So from the point of view of this system, you do this here, see, and you do this here. But then you don't do it anymore because there is always some imaginary component.
I see. Yeah, I asked you this question because I also have this same kind of plots, but in some wildly semi-metallic phase, non-Hermitian, of course.
Yeah. No, it's it's just here.
Okay. Thank you.
Thank you. We have another question from YouTube, which I believe refers to the third part where you had where you mapped back to this reservoir engineering approach and where you had the coherent and dissipative coupling split up. And the question, there are two questions from YouTube. And the first is if the Hermitian part of the Hamiltonian alone is retained and the time reversal symmetry breaking term is included, will that give a non-trivial winding number? And then the second part of the question is, how is this winding number different or related to the winding number in complex energy in the complex energy plane that one gets after retaining the non-Hermitian part too?
Okay, so let me go there. So the question is, if I don't have this one and I define this winding number, so okay, I guess it depends on what is meant as a winding number in this context, because let me say, the winding number that is discussed in the context of non-Hermitian, the non-Hermitian skin effect, it's a winding number in the complex energy plane. So if I now remove the non-Hermitian component, and this is just a line, there is no K dependence. If I remove the non-Hermitian component, the winding number loses any meaning. So, but I imagine that maybe the reference is to the winding number that we are, for example, defining in the context of the SSH model. So here that winding number is also not really well defined because, in the SSH model, we write down, I don't know if I can annotate from here, but we write down, a 2x2 Hamiltonian, and then we take the term that is multiplying the sigma x and sigma y component, and we look at the winding. But that requires a unit cell with two sublattices, and this model is much simpler than that. So here I just have one unit cell and there is that macro spin. So this winding number is not really well defined here.
Okay, thank you for answering the YouTube question. Maybe I could just ask one question before we close. I was also wondering in the first part of the PT-symmetric SSH model where you showed that you get some unstable modes, and then you showed the simulation where you see that there's basically one current that survives. And I was wondering if I can understand this in such a way so that the unstable modes, I think it's in the first part, not the one on the 2D skin effect.
Is this one?
This one, yeah, exactly. So I was wondering, so I was wondering, is it the case that the edge, so the edge state, the frequencies corresponding to the edge states also have a positive imaginary part, then the system in principle would be dynamically unstable. So then I have to consider the nonlinear dynamics, and then I can see the lasing transition. Is this what I should think of? Okay.
Yes. Yeah, no, it's exactly that. So I wish I cannot make animations, but I think if I were able to, that would make it much clearer. So here you have like some magnetic ferromagnetic element, for example, and you like tons of spin, but imagine it just like a big spin. And what you're doing at one edge, so one edge is A, the other is B. At B, you're not injecting anything, but at A, and actually you're doing it in all the A, you're putting a lot of spin current in the system, so that's exerting a torque, and you know, it's actually quite strong torque. So, and you're absolutely right. The quadratic Hamiltonian makes sense when this torque is tiny, right? So the deviation is small, and you can really think about just linear. But actually, what we are doing to create this PT symmetry is to put a quite strong one. So yeah, that's also why you really should look at the nonlinear dynamics. And that this is just telling you that everything is like inert, but this one starts doing this.
And then related to this, have you seen or looked for synchronization in that regime?
No, that's an interesting question. We didn't look at that.
Yeah, but very interesting. Okay, thank you very much, Benedetta, for this very interesting talk.
Thank you.
I think this is a great way to conclude the seminar series before our holiday break. So enjoy the holiday season, everyone, and see you in the new year. Thank you very much for joining today.
Thanks a lot. Bye.